My esteemed listeners, my esteemed viewers, in this tutorial we clearly explain CRC, that is cyclic redundancy code, an error detection mechanism, and this tutorial comes as a sequel to tutorial number 1, wherein we have discussed the essentials of the link layer protocols. And cyclic redundancy check is a robust method and a sophisticated method of detection of errors that may happen in the frame, and it has a name. The meaning of this cyclic redundancy code is in the name itself. It generates the code, that is a group of bits. Bits here are referred to as codes, ones and zeros. A group of bits are used and they are generated in this code, through this code. Therefore there is a code, mention of code, and redundancy, and these codes generated are exclusively used to find out whether or not error has happened, and these codes will be placed in the trailer of the frame. And it is cyclic because the cyclic terminology comes from the fact that these codes, the redundant codes, will be found out through a cyclic procedure, that is modulo 2 division. Therefore the name. Therefore cyclic redundancy check or cyclic redundancy code has the entire procedure hidden in the name itself. It is something like this. Let us say 9 is the data that is to be sent. Simply explained, cyclic redundancy code can be understood like this. Let us say 9 is the data that is to be sent across, and the sender will divide this 9 by 2. Then this is dividend and this is divisor. When 9 is divided by 2, what we get is 2 4s are 8, 4 as the quotient and 1 as a remainder. Then sender will add to the data the remainder, okay, and it will become 10. Now 10 is sent to the receiver, okay, 10 is sent to the receiver, and along with this 10, the generally agreed divisor will also be sent. Therefore the receiver will be dividing this 10 by 2, and if he doesn't get any remainder, then nothing has happened to the data. If he gets remainder over there at the receiver's level, then definitely it's going to be assumed by the sender. Presumably errors must have happened. Therefore this method is a sophisticated method because it can identify any kind of errors that may happen, or the errors of any length also. It's an error detection mechanism or error detection technique, as told earlier. It is widely used in today's computer networks. And CRC codes are also known as polynomial codes, since it is possible to view the bit string to be sent as a polynomial whose coefficients are zeros and ones, and values in the bit string, with operations on the bit string interpreted as polynomial arithmetic. That means the data which is in the form of ones and zeros can be converted into a polynomial, and the procedure involves selection of a polynomial which is standard, and the data in the form of a polynomial will be divided by the generally agreed divisor, that is also called as generator polynomial, and the quotient is generated and the remainder is generated. Then to the data polynomial the remainder is added, and the data plus added remainder will be sent to the receiver, and receiver will once again divide the things that have been received by the sender by the generally agreed upon generator polynomial, and if the receiver finds no remainder, then nothing has happened. It is presumably taken as no errors have crept in. And if there remains to be if this data generates some kind of a remainder, it is understood that errors have happened. Now, it is a polynomial can be converted into a bit string, and a bit string can be converted into a polynomial. Let us say this is the polynomial x to the power of 7, x to the power of 5, x square, x plus 1. So in place of 7, 1 is placed, and in place of 6, because it is absent, it is 0. X to the power of 5 is present, it is 1. X to the power of 4 is absent, it is 0. X cube is absent, 0. X square is 1. X is 1, and the constant term is 1. Therefore, the number of bits in the data stream represented as a polynomial, vice versa, will have one extra bit. This extra bit is devoted to the constant term. And in the same token, x to the power of 7 becomes 1, x to the power of 6 is 0 because it is not present, x to the power of 5 is 1, x to the power of 4 is 0 because it is not present, x cube is absent, therefore 0, x square is present, 1, x is present, 1, and 1 is present. There is a constant term that is present, therefore this polynomial x to the power of 7 plus x to the power of 5 x square plus x plus 1 is a representation of this particular data stream. And let us say the advantage of representing a data stream, the bit stream in the form of a polynomial, has its own effects. There is a good advantage, there is a significant advantage, because such a longer stream of data, stream of bits can be represented succinctly or cryptically in the form of a short polynomial. Look here, this is x to the power of 15, so it is present. So at the 15th place, at the 16th place, because there is one place that is to be left around for the constant term. So if 15 is the degree of the polynomial, then there will be 16 bits, and one bit, the last bit, is devoted to the constant term. So x to the power of 15 is 1, x to the power of 14 is 0, x to the power of 13 is 0 because of the absence of those terms, x to the power of 12 is 0, 11 is 0, 10 is 0, 9 is present, therefore it is 1, 8 is 0, 7 is 0, 6 is 0, 5 is 0, 4 is also absent, 3 is also absent, 2 is present, and 1 is absent, and the 0th term is also present. Therefore, such a small polynomial, succinct polynomial, can represent a huge length of a bit stream, and it is known that the cyclic redundancy code is a typical polynomial division, and it is implemented in polynomial circuits. And similarly, in the same token, a bit stream can be converted into a polynomial. 1, 2, 3, 4, 5, 6. Okay, 6 bits are present. Therefore, the degree of the polynomial must be 5, because one term should be devoted for this constant term. So x to the power of 5 is present. There are 6 bits. Therefore, degree of this polynomial must be 5. So x to the power of 5 is present. X to the power of 4 is absent. 0 into x to the power of 4, 0 into x to the power of 3, 1 into x square, and 0 into x to the power of 1, and 0 into x to the power of 0. So it reduces to, see, this is how it comes, and it reduces to x to the power of 5 plus x square. So this is the polynomial with only 2 terms representing such a huge length, 1, 2, 3, 6 bits. Therefore, polynomial division and the implementation of cyclic redundancy code in the form of a polynomial division, okay, comes very handy. And for the sake of clarity, since CRC is based on polynomial division, we will literally do a division. Let us assume that 3x cube plus 2x square plus 10x plus 20 is the polynomial, which is the dividend, and x plus 3 is the divisor. This is also called as generator polynomial. This we cannot choose generator polynomial according to our whims and fancy. Of course, it comes like our this thing, industry standards. There are generator polynomials, okay, given by the industry standards. Okay, that only we are supposed to use that. Okay, 3x cube plus 2x square plus 10x plus 20, and we will divide this. In order to generate this particular term, we need to multiply by 3x square. So 3x square into x, 3x cube, 3x square into 3, 9x square. Then we will minus this, as we know, okay, just like a ordinary division. So 2x square minus 9x square is equal to minus 7x square plus 10x will remain as it is. Now this is to be generated. Therefore, in order to generate this, we need to multiply this divisor by minus 7x. So minus 7x into x minus 7x square minus 7x into 3, so 20 minus 21x. Now this one will cancel, leaving behind 10x minus of minus 21x. Therefore it gives us 31x, and 20 is let to come down. So 31x plus 20 remains. Now in order to generate 31x, we need to multiply this divisor by 31. So 31 into x, 31x plus 31 into 3, 93. So what it gives us is 31x and 31x will cancel, and what we are left with the remainder, which is equal to 73. And the 73 is to be added. The 73 is to be added for this. Therefore it is 20 minus 73. Actually 20, the existing thing, minus 73, since we are supposed to add this remainder. So what we get is, okay, it is wrong. It is 3x cube plus 2x square plus 10x plus minus 53. Okay, this is what which remains. And now if this is sent to the sender, if this is sent to the receiver, and if it is once again divided by x plus 3, then what we get is 0 remainder. This is the analogy of CRC. Now CRC procedure, how exactly CRC procedure is implemented on bit strings directly, and we will do that. We will take that into consideration. Consider a d-bit piece of data. D-bit piece of data, let us say 10 bits, 12 bits or 16 bits or whatever. D. This data is called as capital D, that the sending node wants to send to the receiving node. Okay, the sender and receiver must first agree on r plus 1 bit pattern, that is a divisor. This is also called as generator or generator polynomial, r plus 1 bits. Therefore, where r is the degree of the polynomial, degree of the divisor, r is the r plus 1 bits, known as the generator, which will be denoted as G. For a given piece of data D, the sender will choose r additional bits. The data containing D bits will be appended with r additional bits, where r is the degree of the divisor, that is degree of the generator. R is total number of bits minus 1, that is r number of bits. It will be added, it will be concatenated, it will be added literally, and r, this will become r, and append them to D such that the resulting D plus R bit pattern is exactly divisible by G using modulo 2 arithmetic. Now, the process of error checking with CRC is thus simple. The receiver divides the D plus R, D contained in the data, R number of bits, because we have chosen R plus 1 bits for as a divisor bits. So D plus R. If divisor bits consists of 4 bits, then we have to append 3 zeros with the bits available in the data D received by bits by G. If the remainder is non-zero, the receiver knows that the error has occurred. Otherwise, the data is accepted as being correct. All CRC calculations are done in modulo 2 arithmetic, as I told you earlier, without carries in addition or borrows in addition, in subtraction. This means that addition and subtraction are identical and both are equivalent to the bitwise exclusive OR, because 1 plus 1 and 0 is 1, 0 and 1 is 1, 1 and 1 is 0, and 0 and 0 is 0. And for generator polynomial, we use standards as per industry standards. CRC 8 is there. This will have 9 bits, and this will have 11 bits, this will have 17 bits, this will have 33 bits. So this can take care of any huge amount of data, because this is a divisor polynomial. Anyway, this should be converted into bit string, and the available data is already a bit string. Append to that here 8 number of additional bits, here 10 number of additional bits, here 16 number of additional bits, 32 number of additional bits. because the number of bits over here is equal to r plus 1, that is 8 plus 1, and here it is 10 plus 1, this is 16 plus 1, 32 plus 1. Okay, the data bits are to be appended with number of zeros which is equal to degree of the divisor polynomial, degree of g. Okay, now we will take a example. So we will once again explain data, of course, data is d bits, data is d bits, let us say 16 bits, and add to that, append to that r 0 bits, where r is degree of the generator polynomial. Okay, if the degree of the if the polynomial, if the bit string has 4 bits, okay, if the bit string which is called as a divisor has 4 bits, then we have to add 3 bits. Then the next step is, then the divisor will consist of r plus 1 bits. We have to choose this is by industry standards, as I told you earlier. Now next, perform modulo division. While we divide a bit string by another bit string, okay, upon every step, in every step we need to subtract. Subtraction is XOR and also addition is also XOR, right? Remainder will be R bits. Consider upon division, finally whatever the remainder that remains, you consider only R bits. Okay, this is CRC. The remainder itself is called as cyclic redundancy code, and this code is added to the data and it is placed over here and it will be sent. The data plus CRC will be added at the receiving end. This and this will be added and it will be divided by the agreed upon the divisor, that is generator polynomial. And if the receiver gets no remainder, then it is supposedly no errors have happened. And if it generates remainder at the receiving end, then definitely some errors must have crept in. Okay, let us say this is the data D 1 0 0 1 0 0. We are taking an example literally, and we will do it, work it out. And this is the divisor polynomial 1 1 0 0. Since it has 4 bits, the degree must be 3. Degree must be 3. R must be equal to 3 here. R equal to 3. R equal to 3. So now this is, therefore we need to append 3 zeros over here. Okay, this is the original data, D bits. Up till here it is D bits. Okay, and this is R bits. R bits, R 0 bits. Okay, precisely. Okay, now perform the division for the sake of generating remainder CRC. Now this is the divisor and this is the dividend, the data plus R bits, and it is to be divided, and we will literally do that. Okay, so 1 1 0 1 1 za. Okay, so here comes 1 1 0 1. Okay, we need to subtract. In general division operation we will subtract, but here we will do XOR. Okay, XOR for addition, XOR for subtraction, because no borrowing is to be carried or no carrying is to be done. Okay, 1 1 1 XOR 1 is 0, 0 XOR 0 is 0, 0 XOR 1 is 1, and 1 1 is 0. You can just simply avoid this, it has no use. And now you just take this 0 down, so it becomes here 1 2 3 4, then 1 za, 1 1 0 1 1 za. So 1 1 0 1. Now once again subtract, XOR 0 1 1 0 0 0 0 1 1 1 1 0. So simply avoid this, then it is no use, and we will let this 1 come down and attach to this, so it becomes 1 0 1 1. Now once again 1 1 0 1 1 za. So we are generating quotient over there. Okay, 1 1 0 1. Okay, we will subtract once again. 1 XOR 1 is 0, 1 0 is 1, 0 1 is 1, 1 1 is 0. Neglect that. then allow this 0 to come down, so 0. Okay, next ones are, so 1 1 0 1, ones are 1 1 0 1. Once again you subtract 1 0 0 0, then allow this 0 to come down, 0. No, it will never go, therefore you put 0 over here. Once again allow this to come down, it becomes 1 0 0. Anyway, this is also not divisible, therefore put a 0 over here, and this is the remainder, because there is nothing that remains in order to bring it down, therefore this is the remainder. 1 0 0 is the remainder. Now take the data, that is 1 0 0. This is what sender will do, 1 0 1 0 0 0. He will send this data along with this remainder. At the receiving end, this will be added, 1 0 0, it will be added, so it becomes 0, again exclusive OR, 0 0 plus 0 1 is 1 1 0 1 0 0 1. Now what remains with the receiver is this. The receiver will once again divide by the generally agreed upon divisor, that is 1101, only not to get any remainder. If the receiver doesn't get any remainder, that means no errors have been crept in. If there is a remainder, okay, which comes on this division, once again at the receiving end, definitely errors must have crept in. Then error correction mechanisms will take place and errors will be corrected. So this is essentially CRC. Okay, we have generated these codes over here, they are redundant. Okay, this is redundant. Of course 100 is a redundant and it will be placed in the trailer, and this has been generated cyclically by dividing in an iterative basis. Okay, therefore the name, and this is one of the robust methods, because the generator polynomials that are given by the industry or that is being used can cover any length of the data. So with this, I think we come to an end of error detection mechanisms that are available in data link layer. Okay, so with this we conclude tutorial number 2, and in tutorial number 3 we will discuss about media access control protocols. Okay, until then, bye, and if you liked this video, kindly subscribe to my channel. Thank you.